Good morning to all. I am Dhanush. This is our project mate, Abhi, Ananda Sridharan, Dhanush, Krithi. This is our mentee, Dr. K. Satish Kumar, Professor of Department of Aeronautical Engineering in Air Institute of Electrical Technology. This is our topic, the effect of short skewing injection percentage with respect to main flow of TVC nozzle. This is a list of content in our project: abstract, introduction, literature review, project gap, objective, research methodology, design, analysis, result, conclusion, and reference. This is our abstract. The study examined the effect of injection pressure ratio of short skewing nozzle with respect to the main flow thrust vector control nozzle performance and focusing on the nozzle flow dynamics. In this, the thrust vector control nozzle requires precise injection pressure control to achieve optimal deflection and stability of the nozzle. This is our introduction. The thrust vector control of the techniques to allow the vehicle to control in attitude and angular velocity by changing the direction its engine thrust. The thrust vector control nozzle is the nozzle that can be adjust the direction of the thrust of the engine and motor to control the attitude and the angular velocity of the vehicle. In this, the nozzle used to asymmetric fluid injection to create the asymmetric pressure loading to the nozzle surface. In this case, the primary exhaust fluid to be thrust vector. This is the literature review of our project. We taken 9 literature review for our project. It is very useful to us. This is our research gap. The proposed system is exercised improve the mixing efficiency compared to the existing system to the thrust vector control nozzle by using fluid throat skewing techniques in the throat vector control in the nozzle. The gap: fluid throat vectoring will be implemented by the varying throat injection pressure ratio with respect to main flow thrust vector control. Our project idea is to study the jet mixing and jet flow development to the throat skewing nozzle by varying the injection pressure for the throat skewing, maintaining constant pressure at the exit of the nozzle. This is our project objective: to study the mixing characteristics of skewed throat thrust vector control nozzle by varying the throat injection pressure ratio and constant pressure ratio of the shock vector injection. The throat skewing injection pressure ratio is 25%, 50%, 75%, and 100% of 5 bar with respect to main flow thrust vector control nozzle. This is our research methodology: dimensional calculation, design, mesh analysis, set of boundary conditions, CFD pre-processing, solver and iteration, post-processing, result and conclusion. This is our design parameters. A parameter of the nozzle type: convergent and divergent nozzle. Inner diameter is 20, exit diameter is 13, throat diameter is 7.7, convergent length is 35 mm, divergent length is 30, nozzle length is 65 mm, nozzle thickness is 5 mm, domain length 260 mm, and Mach number taken as 2. This is our 3D diagram of skewing nozzle. In that, we are injected a throat skewing injector is in throat section, and exit of the nozzle we have injected the injector. This is our mesh diagram. This is a mesh. This is a deep meshing from exit of the nozzle to the domain. We have given we have elements of 14 lakhs elements we have meshed, and 12 lakhs 22 lakhs of nodes is also where a tetrahedra meshes were used. In that boundary condition of this nozzle, the location of the boundary is body, the domain is fluid, material is air ideal gas, and reference pressure is 0 atmosphere. Boundary condition of CD nozzle is heat transfer, total energy, and shear stress transport. Boundary condition of CD nozzle and the supersonic flow, we have taken total pressure of the mass and momentum, turbulence is all medium, and heat temperature is total temperature. The boundary condition of the nozzle valve, we have taken valve, the location of the nozzle, boundary details smooth defined. The boundary condition of the nozzle inlet is, we have taken relative pressure as 5 bar, we have taken heat transfer as 300 Kelvin. The flow regime of the nozzle outlet is supersonic, and the location is the domain where relative pressure is of 1 Pascal. This is our result of the project. The centerline profile is, we have centerline total pressure contours, this one. We have in that, this is a free jet centerline graph. This is our Mach number contour graph. In that, we have streamline flow is exit. In this Pitospheric tube, the flow is in the constant at the pressure of 5 bars. It has a streamline. In that we have changes. We have according to the variation of Mach numbers. The pressure is going up and down. After that is the result will be in a streamline flow. This is our counter central Mach number. This is the radial total pressure. In this is our streamline flow, free-jet nozzle. In that, this is a expansion and compression of the flow. With the briefly we have noticed here. In that in this image we have to calculate the Mach number at a peak of that. This is a compression and expansion waves are created in there. This is also the center line of total pressure of the tube of by 5 bar. This is an example of 100% of the flow will characterize streamline flow, and that it is going downward direction. The expression of the flow will be detached. This is a density gradient of contour plots. This is our shock waves created in this exist nozzle. This is a free jet and this is air injected nozzle. This is a counter plot of the 5 bar at. This is a free jet of Mach number. This is an injected jet. We have deflection of the exist nozzle. It is created. In this total pressure, the counter pressure ratio is 5 bar of the total pressure is a free streamline flow is detached. In that some angle of deflection will be changed. This is a radial graph of x by t is 0.5. This is a free jet nozzle. The output is in circular motion. In that we have find some face-like structure or mouth-like structure will be created at the